Hi everyone, my name is João Fonseca and I'm here to present end-to-end interdomain network slicing, making use of the 5G growth platform to ensure communications between 5G growth and the 5G VNIP platforms. The motivation for end-to-end interdomain network slicing came after realizing that verticals rely on communication service providers and network operators to have access to communication services that allow for interacting with different vertical resources which may be in different network domains. This means that the verticals, when they are requesting a communication service, want some sort of KPI to be fulfilled, and therefore this communication service is translated into a network slice of one of the three types: enhanced mobile broadband, ultra reliable low latency, or even massive type machine type communication. So following this type of slice may be able to provide access to the vertical resources that are in those network domains, but this network slice normally has a cost, and this cost is defined by network operators and communication service providers, and therefore verticals are not able to negotiate themselves the cost of the communication between the two domains or three domains that may occur. As such, we want to create the possibility for verticals to request themselves the network slices from the communication service providers, making use of network slices as a service, which was theorized by 3GPP. The vertical is then allowed to create itself a communication service which comprises or is translated into different network slice requests that are granted upon some business deals by each of the communication service providers. These network slices will allow for the access to the networks where the vertical resources are being orchestrated. The 5G growth project already allows verticals to request communication services directly from their 5G growth vertical slicer. The 5G growth vertical slicer allows for the request of communication services that, following the vertical's KPIs, delivers them a vertical slice which follows a specific service type. This vertical slice is nothing more than a network slice. As we know by 3GPP terminology, a network slice can have several network slice subnets associated with it. This means that a network slice of a certain service type might have several network slice subnets which might be in different operators' domain. The 5G growth project only supported in its initial form a single domain for requesting these network slices. Therefore, it was possible to request a network slice from the given network operator, and through it make sure that the vertical is able to assess their vertical resources which might be present in a virtualization infrastructure service provider. After this, the vertical is not only able to control the vertical resources, but also manage the life cycle on the operations associated with these resources. A second iteration of the 5G growth vertical slicer allows verticals to request vertical resources from different domains. This is done making use of two domain drivers which are used at the vertical slice level. This means that the vertical can now request a communication service directly from the vertical slicer, which is then translated into a vertical slice. in the process of deciding which network slice as a service solution the vertical needs, the vertical slicer will check up which are the domains associated with the or needed by the communication service. This means that the vertical is can before starting the communication service request can decide what are the domains it wants to connect to. And given that it has the vertical slicer as the associated drivers to interact with the slice managers, it is possible for the vertical slicer to request to the communication service providers for network slices. This means that this vertical slice will be making use of two network slices. In this case, they are both network slice subnets of the vertical slice directly from each of the communication service providers. In this case, the service providers that will be testing are the 5G growth platform and also the 5G VNA platform. Therefore, we will be making use of two domain drivers, one that allows for the request to the 5G growth platform, in this case specifically to the slice manager OSM, which is present in the in the Telecommunications Institute facilities, and the other driver which connects which allows for the request of slices, slice manager of the 5G VLAN platform, in this case SONATA. Therefore, the vertical is able to access vertical resources which are present both in the virtualization infrastructure service providers of two different domains. After this, the only thing that is left to do is making sure that these two slice subnets are stitched and that the access to these vertical resources is made in a secure way using a common communication channel. Here we can see the testing environment, where we can see that the 5G growth domain will be using OSM as one of the subslice subnets orchestration, as well as the 5G VNA platform as another network slice orchestration. In this case, the SONATA orchestration slice manager orchestration is being used. Each domain is using OpenStack as their virtual infrastructure managers. This means that all the virtual network functions will be orchestrated over this environment. Subnet orchestrations will be interacting with the VIMs to deploy all these VNFs and to configure all the needed settings. The vertical can, through the 5G growth vertical slice, deploy a communication service which is translated into a vertical slice. This vertical slice will allow for the request of two network slice subnets to different domains. These domains are enabled by an OSM network slice manager and 5G VNA SONATA network slice manager. Through these slice managers or orchestrators, it is possible to request the instantiation and configuration of VNFs. In this case, we'll be using WireGuard as the solo VNF for making sure that we can communicate between two vertical resources which are present in two different domains. To do that, we have a network which has access with both domains to which we want to link, or to which the vertical needs to access. In this case, we will be using the vertical on premises as a network which can access the OSM domain and the 5G VNI domain. As I had said before, after the instantiation of the VNFs, we will have only an end-to-end slice, which allows for the communication between the vertical resources that are present in both domains through a single to make sure that the vertical slice is an end-to-end slice over that is perceived as an overlay network. We will be using a WireGuard tunnel, which is a layer 3 tunnel, for also ensuring the secure, making sure that the network is secure. Another way we can test the service that is already running is by changing the parameters of the VNFs which are running on. This can be done via the vertical portal, and we will change the VNFs which are allowing for the communication between the domains. In this case, we are using a WireGuard tunnel and an MTD function. So these are two different VNFs with associated VDUs. So we have 4 VDUs in total and 2 VNFs in each domain. So when you want to change the vertical slice, what we will do is we will get the information from the vertical portal, we inserting the request you want to make. Then this will be forwarded to the vertical slicer, and after some time the parameters will be sent down to the orchestrator where the VNFs are running. So this will allow for the change of the MTD function or the WireGuard tunnel parameters. In this case, we'll be changing only the MTD function and the associated mutation time. So this means that the rhythm at which the ports are changing will increase or decrease depending on the set mutation time. It's worth noting that for most operations, the vertical portal will give some feedback on what is the current status of this network slice or the vertical slice. This means that for the instantiation, modification, or dynamic modification and termination operations, we will get feedback at the vertical slice level. Vertical portal level. Now we will show how this is done and what really occurs when we are running the system. As a first step, we will onboard the user into the vertical slicer or the vertical portal. We will then create a group and associate a user. Then we will configure the SLA parameters, the VRAM, vCPUs, and vStorage associated with the service. Afterwards, we will onboard a new domain. After onboarding, we'll set up the environment to be using network slice service provider and select the driver associated at the vertical slicer level. Then we will configure the associated VM, and we'll do the same to the SONATA domain. We'll also use a network slice provider. Having configured both of them, we'll onboard a vertical service blueprint by starting to adding the network slice templates associated with the domains. Then we'll set up some translation rules, and we will configure some actions to be triggered the first day to get some information from the VNFs. Then we will get information about the MTD function. Afterwards, we will add the activate MTD function, followed add peer function and the activate MTD function. After finishing this onboarding, we can go to the vertical slice to the tenant domain and onboard the vertical slice instance using a descriptor which has been created from the blueprint that we onboarded before. So we are instantiating in the vertical slice service, or the vertical service, and we are adding the parameters that we have set up before on print. Here we are adding some information that will be passed to the OSM domain, where this will be used for the instantiation of the network slice network service associated with it, as well as fitting up some parameters to the network to the VMs. Here we can see the VMs already deployed at the OSM domain, so the instantiation started. And now we are starting the configuration phase. The configuration phase starts when picking up gathering the information from the VNF. So that will be appearing on dashboard. So we will see the get VNF info reaching the slice manager OSM and triggering this if then we will see the same for the get MTD info. The operation should be finishing now. Afterwards, we'll be adding the peers or the peer of the SONATA domain to the OSM domain. And on the other side, the same should be appearing to the thing that the instantiation request has been received by the instantiation is starting. The creation of the service started. Also, the creation of the slice is in instantiation mode, and we are seeing that the VNFs and associated videos are being deployed at the VM. Now the service has finished the instantiation, and the SONATA side is starting the configuration. The SONATA portal won't show any information about the part of configuration, and on the vertical portal, having instantiated the service with the MTD function and the tunnel, we can see that the OTPs will be generated at the MTD function. So, but no traffic will be appearing on the open switch flows until the traffic from the tunnel, from the wireguard tunnel, is redirected to the MTD function VNFs. We also will see that the ports that will be used will be the same until we have the configuration for changing the OTPs and we activate the MTD function. We now have, we can see the peers of the tunnel being connected and exchange information via ping. And we will now change the configuration associated with the MTD function. The service is in the associated state, and we will change the interval of the mutation of that first 1 second mutation period, and we'll set the timestamp for when we want this modification to occur. The vertical portal will show the status of the request and will pass to modified when the vertical slicer signals it has received the modification. So we'll now pass to the OSM network slice orchestration, where you can see that the request has already been received, and we will now see that the request has been fulfilled and the primitive has been run. Although the primitive has been run, no change was seen in the latency, and will now decrease the time of the mutation. We have already set also the timestamp to this new. You can see the latency doesn't change again, and we'll see further later in the results that this is something that has been reported several times. We'll now try the same parameter just to show up what happens, and we can see as occurred. We can see the service running and the activation is done, and but we are using always the same port. And after this gap, where you can see on the OTP port changing as well as the OTPs for the MTD function. And now the traffic tunnel, but the ports of the tunnel are, or the ports that the tunnel is using are changing in real time, considering the configuration properties that we have set before. We can see the flows on both of the machines, the OSM and the VINI MTD sides. Show that the traffic is running through the similar ports that are being shown on the OTP platform. So while running this simulation, we have this, but there is also some other visualization terminal that allows us to see if any sort of threat analysis occurs, but we haven't tested in well checking up the results for the interdomain side if there are any events that are reported. So this should be, and it's done. Here we can see the vertical slice instance that has been modified and is present on the vertical portal. We'll now send a termination request to this vertical slice instance. The status of the vertical portal will now show that it is terminating and the request has been forwarded to the vertical portal. On OSM, we can see that the network slice instances are still running, and upon refreshing we can see that now they are terminating. This means that the associated network services and VNFs will be terminated. This also means that the VMs associated with those VNFs will be removed at the OpenStack. Now, as you can see, they are removed. Moving on to the SONATA platform, we can see that after some time it will also receive the termination request from the vertical slicer, and upon receiving those, it will also request OpenStack to from the OpenStack of the SONATA domain or the 5G domain. We can now see that on vertical portal we have a status of terminated, so the vertical slicer says that the service has been terminated. Now we can remove the service from the results. We'll now analyze the results of the same experience that has been run beforehand, and also with another types of configurations. Here we can analyze the vertical slice operations and the time it takes for them to finish. An end-to-end interdomain network slice instantiation takes up to 8 minutes. The termination of the same type of service takes up to 1 minute, 56 seconds in this case, and the reconfiguration time is in the order of the 43 seconds when we are talking about changing the mutation of the MTD function. This means that on average the most of operations, as we can see, are in the order of the minutes. As we can see by the graph, the OSM level operations take a little bit more time than the SONATA Slice Manager operation. This means that the SONATA is quite more efficient to execute the same type of operations. But although this conclusion could be easy to make, it's important to notice that OSM uses Juju for the configuration, while the SONATA is making use of SSH commands, which are quite more simpler. Nevertheless, the operations executed by SONATA take less time, and therefore, even though they don't give as much information as OSM, they are more efficient. We'll now evaluate the performance of the end-to-end interdomain network slicing mechanism. For that, we will evaluate 4 different testing scenarios. One, where we have only the VMs without any sort of services running, so no WireGuard terminal or no, and also no MTD function running. The second scenario where we are running the VNF with the WireGuard tunnel. This third scenario where we got the tunnel and the MTD function with a mutation time of 30 milliseconds, and the fourth scenario where we got the tunnel plus the MTD function with a mutation time of 100 milliseconds. We can see that without any service running, the throughput is around is almost 1 gigabit. And then when applying the tunnel, we get 800 megabits per second. While after running this service with also the MTD function, we get a throughput of around 600 megabits. When talking about the transmitted bytes, following what happened on the throughput, we can see that on a normal scenario without any sort of service running, we can exchange 70 gigabytes. Upon starting the tunnel, this number goes up to the 6.2 gigabytes, and then after initiating the MTD function, this traffic goes to less than 4.5 gigabytes, which means that the use of the MTD function really affects the way that the traffic is being transmitted. By setting the baseline of the available throughput to a scenario where we can get all the VMs without any service running, and by passing the traffic between the vertical resources through these VMs, we can see that after changing the VMs to running the tunnel, we will be using only 90% of the available throughput. After that, when we enable the MTD function, the available throughput will be then diminished to around 60% of, or according to the baseline. This means that the MTD function has the possibility to severely deteriorate the throughput available of this network slice. Therefore, we should take that in account when we are setting KPIs with the verticals. When talking about retransmission of packages, we can see that when we have a normal scenario, that we have a little bit of retransmissions on around the 0.0225% of packages are being retransmitted. After which, when we start the tunnel, because it is an overlay network, the number of packages that are transmitted, or the percentage of packages transmitted, is reduced. But something interesting happens when we use an MTD function with the tunnel. The number of retransmitted packages will increase, but depending on the mutation time, the number of retransmitted packets, or the percentages of retransmitted packages, will increase. So if we have a higher mutation time, this means that it will be more difficult to get into a consensus, and therefore we will have more packages that are lost. But if we have a lesser amount of time in the MTD function for the mutation, a smaller percentage of retransmitted packages, as we can see here in the graph. Now evaluate how the round trip delay is affected when we start running a perf. So when we have the normal scenario, the latency is quite low, but after starting the tunnel, we can see that we have an increase of latency of around, let's say, 8 milliseconds. And then when we start the MTD function, this effect will get lower. Therefore, we can say that the MTD function has less impact when we have an higher mutation time than when we have a lesser mutation time. So with high values of mutation time, the latency won't be as affected as if we have low mutation times. But by our tests, we can see that so far the tunnel is the most impactful component when we are evaluating latency. As expected, testing the latency between the two vertical resources when nothing is transmitting really proves that the impact of running the tunnel is quite significant, and also when we start the MTD function, and then the latency will increase also. But we now have two factors that we need to analyze. One is what is the impact of running the tunnel, and the second, what is the impact of running the MTD function. We can see that the mutation times actually don't have a really high significance when we are testing only the ping. But while we are running an iPerf to test the available throughput of the network, we could have a higher difference on the latency of the MTD functions. Here it's not so significant as we can see in the figure.